Hey, what's up guys? Sorry I couldn't be there with you today, but at least I get to share this video with you, so that's awesome, right? I'm gonna make two videos together. So today's homework and tomorrow's homework, 9.2 and 9.3 are gonna be all the same video, but I'll let you know when this one ends. So first of all, we're gonna start this one on page 493. 493. And in this section, we're talking about congruence and corresponding parts. And this is a pretty short section. So you guys know what congruent figures are. And if two figures are congruent, then they have what we call corresponding parts. So these two are congruent because DEF is just a reflection of ABC. So if they are congruent, then we want to find which are the corresponding parts. So for instance, side AB is congruent to side DE. Side CB is congruent to EF, and then AC and DF. And if you look in the order that it's written, A corresponds to D. So angle A and angle D go together. And AB would go with DE. So side AB and side DE. So you kind of can look at the order of the letters, the vertices as well. Angle B is congruent to angle E, and angle F is congruent to angle C. And you see that we use these tick marks, so the different ones show which is congruent to which. So these two are the same, so those are congruent. These two are the same, those are congruent. And then with angles, we have the little arch here, and then this one has like a little double arch. So this is congruent to this, and this one with the double is congruent to that one. So that's kind of how we can tell, and how we indicate is with the different kinds of tick marks and angle markings. So again, we would say, though, again, just getting used to some geometry symbols. Triangle ABC is congruent, so the symbol is congruent to triangle DEF. If two figures are congruent, their corresponding sides are congruent, and their corresponding angles are congruent. So again, AB corresponds to DE, angle A corresponds to angle D, so on and so forth. In symbols, we would say that angle A is congruent to angle D, BE, CF. Sides, we use this notation to indicate a side length, a little bar over the top. AB, side AB is congruent to side DE, and so on and so forth. So you should know those symbols. Go to page 494 and let's look at the example and see if we can just label some of these corresponding parts. So these two triangles are congruent and they are marked for us. So we're just going to fill in which ones are corresponding. Okay, so let's see here. Click to highlight the corresponding angular side. So side GH is corresponding to side JK. HI corresponds to, this doesn't look like the same one in the book. Oh, it is. HI, no, corresponds to LK. So they give you this one on the right and you fill in this one down here. And then JL corresponds, or LJ as it's written in the book, corresponds to IG. And then again, angle J corresponds to G, K corresponds to H, and I corresponds to L. So these are the marks used, and those are the congruent corresponding sides. So here they are. If you miss them, you could fill in those blanks. So try, and this is not just for triangles, so this is for any congruent shape. So on page 495, there's a check problem with a trapezoid. See if you can fill out which one is corresponding to which on that check problem. Then you can use congruence to find missing measures of things as well. So in this case, we have two congruent triangles, and we have a measure of one triangle. We want to find a measure of an angle in another triangle. So let's look at this here, and let's just draw this out. So it might be helpful, I would say it might be helpful just for sake of visualizing and not having to get too confused. But it says that triangle CEB is congruent to triangle, or excuse me, BCE is congruent to DF. G. So it might help to draw them in the right order so you can see that D goes with B, F goes with C, G goes with E. So we know side angle they give us angle CEB, which is this one right here. They tell us that that is 50 degrees. And they want us to find, oh my goodness. I always do this. Okay. They want us to find, so this is 50. Ugh, so annoying. Okay, this is 50. And they want us to find FGD, which is this one. Well, E and G are the same. It doesn't matter if we call it FGD or DGF. BEC and CEB are the same thing. So this angle is congruent to this angle right here. And again, if you draw it out, it might be a little bit easier for you to visualize. But CEB and FGD, technically CEB would be, yeah, FGD. So those are corresponding parts. Oops, I went too far. So they are corresponding, which means that if this one is 50 degrees, then this one is also 50 degrees. It's really pretty basic, this section. So try the check problem on the bottom of page 496 and draw me a congruent symbol on the left-hand side of the margin on page 496, and that is the end of 9.2. Okay, so you can pause it here and watch the rest of this the next day. I'm just going to let this run a few seconds so I can tell you when to start the next video. Okay, so now we are in our next section, 9.3, and this section deals with similarity and transformations. So the first two sections of this chapter, we were talking about congruent figures, and now we're going to look at similar figures. Similar figures are something like this, these nesting dolls. I don't know if you guys have ever seen this, but they're very similar, right? They look exactly the same, except one is smaller than the other. So we're going to kind of look at some ways we can tell similarity. This is on page 501. So in your books, you guys will go to page 501 and start taking notes there. The congruence transformations were translations, reflections, and rotations. Whenever you do those transformations, you end up with a congruent figure. But with dilations, we end up with a figure that could not be congruent. If we shrink or enlarge, then we have an image that's not congruent, but it is similar. Okay, so if I look at rectangle ABCD and I look at it with a scale factor of 1/2, it gets smaller, right? With a scale factor of 1, which you don't normally see, it's the exact same image. 1.5 gets larger and 2 also gets larger. So this is a dilation of this rectangle. Now, the size changes and the image and the pre-image are not congruent, but the shape of the figure does not change. So it's still a triangle, a rectangle. They're still both rectangles with the same kind of proportions, but one is larger or smaller than the other depending on which dilation we do. So on page 502, actually before we get to that, let's watch this quick video. So before we get to the video, sorry, I'm skipping ahead. We can show figures are similar if the second can be obtained from the first by a sequence of dilations and transformations. So if I want to see if EFGH comes from EFGH, E prime F prime, or E double prime comes from this, if they are similar, is there transformations I can do to get from one image to the other? So on this, if I dilate it, then I'll get this one in green. So if I dilate this and enlarge it, then we get this one in green. So dilate it by a scale of 2, and then if we move it 3 right and 8 down, then we end up with this one. So this orange is a similar figure of the blue because we were able to use a series of transformations. So again, we'll still be doing these other transformations, okay? But they won't be congruent. So you might do a dilation first or second and then do a translation rotation, something like that. So you guys can watch this and see how we show two figures are similar.
triangle ABC and triangle DEF are shown on the coordinate plane. You can determine if the two triangles are similar by using transformations. First, determine if triangle DEF is the dilated image of triangle ABC. Write ratios comparing the lengths of each side. The ratio of side DF to side AC is 10 to 5, or 2 to 1. The ratio of side EF to side BC is 8 to 4, or 2 to 1. The ratio of side DE to side AB is 6 to 3, or 2 to 1. The ratios are equal. So triangle DEF is the dilated image of triangle ABC using a scale factor of 2. Dilate triangle ABC with a center of dilation at the origin and a scale factor of 2. Next, reflect triangle A', B', C' across the y-axis. Lastly, translate triangle A', B', C' down 10 units and to the right 1 unit so that it maps exactly on a triangle DEF. So, the triangles are similar because triangle ABC can be mapped onto triangle DEF using a sequence of a dilation, a reflection, and a translation.
So this is how we can tell and also figure out what transformations. So this is on page 502, example 1. Let's see if we can figure out if these two figures are similar. So first thing we want to do, and again, DEF is our original pre-image, and then HGI or GHI is our image. So first we want to figure out if it's a dilation. Obviously, if they're not the same size, then we first have then a dilation potentially happens. So what we're going to do is compare side lengths of your image over your pre-image. So we'll take GH, and if we count GH, this is 8 units, which corresponds to DE, which is 4 units. So 8 divided by 4 is 2. GI is 6 units. DF is 3 units. If we divide those, we get 2. HI is 10. EF is 5. If we divide those, we get 2. So if all of these ratios are the same of the side of the image divided by the side of the corresponding side of the pre-image, if all the ratios are the same, then it is a dilation. And this number here is our scale factor. So important to note that you put the image on top and the pre-image on bottom. And if you do that and they're all the same, then that number there is your scale factor. So if we graph this, I gotta close this email, it keeps popping up. Excuse me. If we graph this and we do a dilation with a scale factor of 2, then DEF becomes D', E', F'. And then what can we do? Well, if we translate this now, if I translate it down 3, and right 7, so there's right 7, and here's down 3, then you can see that it maps right onto what was that orange triangle there. So if DEF is mapped onto GHI with a dilation, followed by, in this case, a translation, it could be a rotation or reflection as well, then the two triangles are similar. So see if you can figure out on page 503, you're going to have to divide the sides of your two triangles in the check problem. So first, divide all 3 sides and see if you get the same scale factor. You want to divide the green by the blue triangle. And then if you have determined that they are similar, or if they are a dilation, then see what other transformations you can do to get from one to the other. Here's another example on page 504. So are these two similar? We have 2 different rectangles, and in this case, our original is WXYZ, and we're mapping onto PR or RSPQ. So first thing we're going to do is look at the side lengths for each of those and compare them. So SP, oh, this one is still going over the other way. Interesting. SP is 1, 2, 3, 4, 5. So 5 over, let's see here, 5 over XY, which is 1, 2, 3, 4, 5, 6, 7. There we go. Okay. 5 over 7. PQ, 1, 2, 3 over YX, YZ, 1, 2, 3, 4. So 3 over 4. Okay, and I already can stop right here because 5/7 and 3/4, I don't even have to do the rest of them. We can count how long these are, but these aren't the same. So if the ratios are not equivalent, they're not similar, there was no dilation. So that's nice. If they are different right off the bat, 5/7 is not the same as 3/4, then we know that they are not a dilation and are not similar. So try the check problem on the bottom of page 504. We're going to finish the rest of section 9.3 in class. So that is the end of your notes. And at the bottom of page 504, write down what are your plans for spring break, and I will check that with this homework. All right, have a good evening, afternoon, whatever time it is that you are watching this.